So now I would like to continue. I would like to continue with the more focused on the practices, on the discussion, focusing more on the practices and experience. And we will start with the project, the waste reuse project. And I would like first to ask Professor Konstantinos Komnitsas, who was the coordinator of waste reuse, to introduce us to the project and its main findings. And then we will start with the first session of today's forum.
Good morning. I have to thank Dimitris and Elena for this excellent organization of this workshop. This is a project that started 3 years ago. It's coming to the end. I think we had a very good cooperation and some interesting results. So I will give you a brief overview of the project, and I will say also some things that Technical University Crete was involved in, because we're not agriculturists, we're engineers, so we take the findings of our colleagues and try to do some risk analysis and LCA analysis, which we believe it is interesting. And since most of the day will be devoted to agricultural issues and to waste management, I will give you just different approach of another direction that we followed in the project. So, Waste Reuse project is entitled, it finishes in August, towards sustainable use of agricultural waste and about best practices for agricultural waste treatment and reuse, especially in the Mediterranean regions. Next one goes. So these are the partners. We, Technical University Crete, were the coordinators. We had 4 beneficiaries. Sebas Thesik, if my Spanish is getting better, I think, after so many years of cooperation, from Murcia in Spain, the Center for Agricultural Experimentation and Assistance, CESA, from Albenga, a very nice part in North Italy, west of Genova, LabCam, from the same area, chemical laboratory, mainly responsible for all the analysis, and our friends here in Brussels, Signosis, and I have to thank again Dimitris and Elena for this, this workshop. Go to the next one. So, why treatment and reuse of agricultural waste is required? That's a long, well-known question. The answer is probably not very well known, and we have to prove every time why this is needed in agricultural sector and which are the benefits of its treatment and reuse. So I will go briefly through the presentation. We know that in almost every European country, and especially in Mediterranean countries that the project was focused, there are millions of tons of agricultural waste produced every year. In these wastes, there are useful compounds and what we call recalcitrant compounds, difficult to treat compounds. Some of them are potentially hazardous, and if they're disposed of without any care, they may cause environmental problems, both for soil and for water. So we have to treat them, and it will be best if we reuse them back in agriculture. So we're going to have many, many benefits. Some of them is the production of fertilizers. If we can produce compost, or if we produce organic fertilizers, we save phosphate ores. And some of you may know that phosphate ores from North Africa have quite high radioactivity. So this is another benefit that can come from these savings. Then we reduce what we call the carbon footprint of the agricultural processes. That's what we're trying to do through our LCA analysis. We reduce environmental risks for soil and waters, and especially groundwater in agricultural areas. And finally, we have big water savings, which is very, very important in areas in Southern Europe, in areas suffering from desertification. So that's a big advantage for the farmers and for the society in general. And after all, this is a practice, the reuse of agricultural waste towards this zero waste approach. So within the project, we tried to evaluate innovative and traditional technologies used for agricultural waste management, to develop alternative agricultural practices, cultivation practices, for some crops that are cultivated in South European countries, to protect soil quality from disposal of agricultural waste, to develop a sort of guide involving best management practices, and as I said before, to reduce the carbon footprint and finally increase also the competitiveness of the agricultural sector in South Europe and in general, of course, in Europe. So in the beginning, we started with an assessment of existing technologies that were developed within 49 projects we identified through websites that have been funded from the Commission in various framework programs the last, let's say, 15 years. We could not go back than that because there were no websites available. So we've done a very intensive work to identify these projects, find innovative aspects, see which technologies that have been developed were promising and could be applied, and did an assessment. And based on these technologies, we moved further on to produce our own approach for the project. So we've done laboratory experiments for the characterization of both treated and untreated agricultural waste. We assessed them in terms of suitability for crops, for several crops. We've done a lot of work on soil samples. We assessed 35 soil samples from all the countries, Greece, Italy, and Spain. And also, we assessed extensively 60 agricultural wastes from Italy and Spain, or 30 wastes in each country. I included Alperujo, which is the two-phase olive oil mill waste. In Greece and Italy, we have three-phase waste. There are some differences. I don't want to go into details, but most of the people here know. Pig slurry manure and compost from olive mill waste. So all these wastes and soils were assessed prior to doing all these cultivations in greenhouse and in open fields. So we have three study areas, two in Spain, in Barracks, which is close to Albacete. We had an open field of cereal cultivation, barley and soft wheat, and in Tres Caminos area, in Santomera in Murcia, where we studied, our Spanish school studied the cultivation of tomato and lettuce in greenhouse. The Italian demonstration area was in Albenga, in the Savona province, in the Liguria region, North Italy. Probably most of you know where it is. So in that area, we had greenhouse cultivations of basil, rocket, and lamb's lettuce, and open field cultivations of rosemary, lettuce, and cabbage. You see here some photos of the greenhouse and open field cultivations in both countries, Italy and Spain. The work they've done was very, very good. Since, as I said, for the rest of the day, all the discussion will be around agricultural waste, treatment and reuse, I will give you a brief presentation of our work in terms of risk and LCA analysis. It will be a very brief part. Risk analysis is carried out to assess risk, as we say, for a recipient, for soil, for water, for air, as a result of an action. So in terms of raw materials extraction, waste disposal, and agricultural activity. And LCA life cycle analysis, on the other hand, is used to assess quantitatively, if possible, the environmental, social, and economic impacts during the life cycle of either a process, which may be industrial or agricultural or product. So in terms of risk, we applied a GIS-based approach for the evaluation of potential groundwater vulnerability using a model, a software, which has been developed by the US EPA, Environmental Protection Agency. This software utilizes 7 hydrogeological parameters to determine this vulnerability to groundwater contamination. Drastic is an acronym that comes from these 7 parameters that are used to assess this vulnerability. So it's depth to water, net recharge, aquifer media, soil media topography, impact of the vadose zone media, and hydraulic conductivity of aquifer. So just a brief overview of the approach. So each parameter is scaled by a weighting factor. There are 2 versions of this software, a version that is used in normal situations and a version that is used in situations where there are intensive agricultural activities, so additions of fertilizers, and focuses more on the agricultural sector. So a parameter is assigned a rating between 1 and 10, depending on its class, and then you get a drastic index, so don't have to go into details. So we get 2 different modes, depending on if we use this approach for a normal area, an urban area, for example, and a mode when it is used in agricultural activities. So these are the parameters. If somebody wants more details, I'd be glad to provide them, but there's no need now to go through these details. For example, we get a parameter depending on its characteristics, and we assign a weight. And before we finally calculate the risk, we have to produce several maps. So we need good data to produce these maps, and we're very happy because these are generic maps. We have not copied these maps. We produced them by ourselves with data we got from our colleagues in Italy and Spain and from other organizations, available data. So we produce this spatial distribution of the hydraulic conductivity. This is for the barracks area in Spain. Go to the next one. This is a map that is the agricultural vulnerability map for the same area in Spain. And we see now which areas could be in red, that in those areas the vulnerability is higher. And in order to validate this data, if we go to the next one, please, we see a map showing the nitrates concentration in groundwater. This is actual concentrations received from monitoring wells or from campaigns carried out in the area in the last 3 years. So this data, actual data of nitrates, based the classification and the classes based on the nitrates directive. So the threshold in this directive is that if nitrates is above 50 milligrams per liter, then groundwater is contaminated, so an action has to be taken. So we see that in these maps that our approach gave quite good correlation, had a quite good correlation with the actual nitrates map. It was about 80 to 85%. So we've done a similar work for Albenga in Italy. I'm not showing the same maps. I show you some different maps. Of course, geology is very important. Albenga is a beautiful area for those who have been there. So the mountains come to the sea, so there's a narrow lane of fertile land where agricultural activities take place. So geology is also important. And the next map, please, is about the hydrographic network, which is also very important to take into account all this data and calculate the risk. And next one, please. So this is a land cover map that was produced from information available in official Italian websites. The next one, please. This is the distribution of hydraulic conductivity. We see that in most of the area is pretty similar because it's a coastal area. And this is the relevant vulnerability map for groundwater in the Albenga area. So we see that most of the Albenga area is under high risk class because of the intense agricultural activity that takes place there and the high application rate of fertilizers, chemical fertilizers. In this picture, this map, there is a different variation of this vulnerability map. It's a different approach that uses a different index that gives more emphasis on the land use parameter, which is very important. Land use is very important and affects also the quality of groundwater and the impact that some activities have on groundwater. So this is a different variation of the map, which is pretty similar to the other one. So just a brief introduction to life cycle analysis. Life cycle analysis, some of you may see many. The important aspect here is to have reliable results. And how do you have reliable results? Reliable results you have if you consider the complete life cycle of a process. So what we've tried to do here, we took a boundary that covers almost everything. So even from transport of fertilizers, transport of compost, all the processes that were involved in this agricultural, in an agricultural cultivation, and also the whereabouts of the waste. So we're not restricted to only, let's say, okay, I get the waste, I do not care what happened before I got it. I do not care about these emissions for its production, the production of compost, so I take it and use it. So we started from point zero. How was this waste produced? Which were the emissions during production? We gave a big effort to calculate the impacts of waste application, because in order to apply waste, you have to transport waste, you have to use tractors, you have to use everything in the farm to calculate all the emissions related with this waste application. And in the end, what happens if you have more waste, and what do you do with them? So it's a complete life cycle. We hope that we have reliable results, and this has to be tested, still has to be tested. But we've done what we could best in this project. So just to have a look, we have going to the next one, Jens, going to the next one. So it's the production of a crop that includes the compost production, the compost transport. If we're going to take into account this greenhouse cultivation, we have to think also about nursery transport, the young plants, and apart from the production of a crop, waste utilization and waste transport, and then which is the final product. So it's a big exercise, needs a lot of data. Sometimes it's difficult to find all this data, and you have to assume. For example, if you transport compost from Brussels to Louvain, do you transport it by train? Do you transport it by truck? So this affects a lot the process in terms of LCA. So you have to know what happens in every case. So I'm not going to, just a couple of more slides. So you can get these graphs by taking into account the most important parameters that are considered for an LCA study. So this is the acidification potential, the eutrophication potential, the global warming potential, the ozone depletion potential, the photochemical ozone creation potential, and the cumulative energy demand. I could show you tens of these graphs, but I will show you only you. So we see in each case, in each country, for example, which is the effect of each agricultural activity, either in greenhouse or in open field. For example, agricultural fertilizers production, fertilizers transport, machinery, waste transport, all these activities in the percent calculation, percent contribution to the overall impact. So from these graphs, if they're accurate, so decision makers, policy makers can have a look, and of course scientists, and say, if we have a big contribution to a specific impact category, what can we do to reduce this impact? This is the most important part, I think, and if the data are accurate, then we can really take very, very good discussions to minimize these impacts and improve what we call towards sustainable agriculture. Go to the next one, please. I think we finish. This is a very important part of the project, and for this part, our friends in Signature are responsible to develop this code of waste management best practice. So this is something that will be a delivery of the project, which will be useful for many stakeholders. So based on these experimental results, based on the outcomes of LCA and risk analysis, to develop this code, which should be brief and accurate and precise and that somebody can trust in, which are the best practices in terms of agricultural waste reuse and in general management. So the code will provide decision-making tools to policymakers towards a more sustainable agriculture, not only for South Europe, where we come from, but for the entire agriculture, all the countries in Europe. So conclusions, just very briefly, we believe, based on our results, that agricultural waste can be treated and reused, and our partners will give you more data later today. From our part, we believe that if we link this data with risk analysis and LCA analysis, we can have a much broader framework which covers the entire sector and gives us, I think, a good view of all these processes we study. And we do believe towards the end of the project that, yes, agricultural waste can definitely become a resource and provide many benefits for the sector. I think this is the last one. Thank you. Thank you very much.
Thank you, Kostas.